This video will introduce our paper Beyond Blur, Real-Time Ventral Metamers for Foveated Rendering. Our goal in this paper is to improve foveated rendering using advances in vision science. We aim to go beyond foveated rendering approaches which simply reduce the resolution with distance from the fovea. This results in an image that is blurry in the periphery. We instead draw from vision science, producing a metamer to the true image. Two different stimuli are metamers if they are different, but are experienced as being the same by a human. Here we produce images which look the same as a reference for a particular fixation point, here the center of the image. A traditional foveated image would devote more of its resolution to the fovea and less to the periphery, for example by using a radial mapping at a lower resolution, as shown here. This is more compact for compression applications, and faster to render in rendering applications. However, the result is blurry in the periphery of the image, and this is very noticeable. We instead present a representation based on pooled statistics of an oriented image decomposition, the steerable pyramid. These are still very compact, but are able to capture these missing higher frequencies in the periphery. Conversion between images and our foveated representation is extremely fast, meaning it is suitable for real-time rendering on high-resolution HMDs. Our main contribution is a compact statistical model from which we can generate metamers to a reference image. In contrast to previous research on image metamers, both analysis, extracting the representation, and synthesis, generating an image based on representation, are efficient and parallelizable. Here we render a 3D scene, and we are able to apply both analysis and synthesis to every frame in real time. We show the following recordings taken from the Varjo XR1 head-mounted display. This display features foveal inserts, small displays at the center of each eye display with a higher pixel density. The following videos are captured by a camera pointing towards one of the lenses in the HMD. This video shows an application that displays a 360-degree equirectangular image through the headset. The image is processed by our analysis and synthesis processes every frame at a fixation point programmed to cycle around the center of the image. The location of the fixation point is indicated by the red circle which fades in and out. This application applies both the analysis and synthesis portions of our approach in real time for every frame rendered, demonstrating that both can be performed in real time at the resolution and frame rate required for a modern HMD. Our first user study presented Landolt symbols to the user at varying angles and eccentricities. These symbols were either unchanged, blurred with a number of different blur settings, or processed using our Metamer model. We found that task performance was better using our Metamer stimuli than when applying higher levels of blur. Our second user study tested users' preference between 360 equirectangular images treated using three different approaches: blurring of the periphery, metamers generated using our model, and metamers generated using an existing model from the literature. We found that our metamers were preferable to those generated using the existing method of Freeman and Simoncelli in this setting. For our final user study, we presented 360 images composed from two images, bisected at a random angle and blended together across the boundary. One image was treated using a foveation method, and the other either also treated with the same method or replaced with the reference image. Our goal was to see if users could identify when images were consistent or inconsistent. We found that our method was rated as consistent at a higher rate than the other foveation methods compared. Our foveated image representation is compact and compresses efficiently, opening up potential applications in remote foveated rendering and foveated video streaming. We compare our approach to applying JPEG to the reference image and to applying JPEG to a reference after applying a blur to the periphery. We note that we avoid the artifacts present when compressing to a similar size using JPEG. Applying JPEG compression to an image which has been blurred gives acceptable results at this file size, but the periphery naturally lacks the high frequencies which our approach preserves. For this application, we demonstrate how our model can be used to reduce bandwidth requirements when using the high-resolution textures required by modern HMDs. Typically, when sampling from a texture, MIP level is selected based on distance from the camera alone. This means that if an object is sufficiently near the camera, the highest MIP level will be sampled, even if that object will fall in the periphery of the user's vision. We exploit our Metamer model to allow us to sample from lower resolutions of the statistics maps, saving bandwidth without a reduction in perceived quality. We train a network to accept a noisy path-traced foveated image as input, and to attempt to recover our foveated image representation as its output. This can then be synthesized into an output image. We compare this to a baseline approach which simply trains the network to recover the ground truth noise-free image directly.